Hi, Vicky.
Hi, Shane.
When was the last time you looked outside at the natural world and thought, yeah, that's math?
Well, probably never now that you mention it. Like I've never had that thought ever.
When thinking about this, one thing that in the day job, or the whole idea of like science communication and storytelling in particular, is that I constantly tell folks that science is all around us, that it affects each and every one of us, that no matter what we're doing, there's science involved with it. And I never really thought about that could be true with, so many things, but also math, right?
Right.
Technologically speaking, sure, like the fact that we are talking to one another via this Zoom-like interface, there's math there. Natural world, angles of the sun, how temperatures work, I don't know. What else? Let's make a list.
Angles of the sun, though, makes me think of like the only thing that maybe comes to mind is like, when did you learn in school how to like calculate, maybe I'm even getting this wrong, the height of the tree by the length of the shadow or where the sun is something. I don't even remember what it is. I could just picture the little drawing in the textbook.
I can picture the drawing as well. Yeah. Well, no, that's really good because even though that we can't remember even the specifics, and I feel like folks have a really sometimes negative relationship with math.
Right.
Something really stuck with us. So
the little drawing.
There you go.
Yeah.
Win-win for math and nature. Science is fascinating, but don't just take my word for it. Join us as we hear stories from scientists for everyone. I'm Shane Hanlon.
And I'm Vicky Thompson.
And this is Third Pod from the Sun. So math may have a negative reputation with many folks, but it's such a powerful tool. Today, with our producer, Jessica Buser-Young, we'll hear about scientists who use math to calculate the future of our planet. Hi, Jessica.
Hi, Shane. Yeah, these scientists are known as climate modelers, but no, not like America's Next Top Model. That's what I thought, but these folks, they have the ability to mathematically describe complex natural systems and climate transitions.
Oh, and it's sure a good time to talk about transitions in Earth's history, given the current climate crisis, right?
Oh, absolutely. And climate modeler contributions are critical to understanding climate science and directly assessing policy decisions. So the impacts of climate change are really undeniably obvious, and these scientists are working to calculate the impacts on humanity and ecosystems. So recently, scientists gathered to confront these calculations in a several months long effort of collaboration in order to understand and predict atmospheric change. And our guest was one of those scientists.
I'm Matthew Huber. I'm a professor in the Earth, Atmospheric, and Planetary Sciences Department at Purdue University. I'm also director of the Institute for Sustainable Future. And what I do for a living is I'm a climate modeler. So I look at past climates and current climate and try and understand what future climate will be like. I guess I would say in all honesty, I wish I was better at math than I am. I'm really pretty poor at it. I've worked over the years with really amazing colleagues who are, by training, either physicists or applied mathematicians, theoretical people. And what I've really done is try and learn from them and try and take what they're doing and either understand the data or more sophisticated models, or in some sense, occasionally what I'm doing is I'm just forcing a confrontation of those things. Sometimes those groups kind of all live in their own reality. And intellectually, as a graduate student, that was the main kind of transition that I made personally, was coming from a theoretical background and working with experts in dynamical systems theory and turbulence and nonlinearity, and they tended to write a bunch of simple equations, and it was all wonderful, but it was sort of lacking in a grounding in an observation. And so then I began working with communities that generate paleoclimate data and working with the communities that develop these more sophisticated big models. And a lot of what I've done in my career is trying to get those different communities to talk together and communicate better with each other.
What do you mean by model? How do you do that?
Yeah, so modeling is a really interesting topic. I teach a course in modeling for people with different backgrounds, and modeling can mean many, many different things to different people. That you can have visual models. A schematic is a visual model. You can have very simplified set of equations. In our case, most of the equations that we might use for modeling the climate system are nonlinear in very important ways. And so you might write 3 or 10 equations and solve them stepping forward in time to represent some basic element of the climate system. For example, how Earth's radiation interacts with surface temperature and the amount of ice on the planet, and how interactions between ice and the ocean and the atmosphere can modulate the temperature of the planet and the amount of ice on it.
What is nonlinear? How would you define that to someone who maybe doesn't have experience in math?
Well, to me, nonlinear means when you write the equation, the thing you're trying to figure out is both on the left side of the equation and on the right side of the equation. So, maybe you have an equation that's like y equals x. Well, that's a linear equation, and you could make that right-hand side of the equation as complicated as you want, and you can still wrap your head around it. But it's a little harder when the equation is something like y equals x times y. And obviously, it was never going to be as simple as what I just said, because then you would just divide out by y. But when the output and the input share something in common, you have an issue that you really need to think about, because what you're trying to figure out, which is usually on one side of the equation, is on both sides of the equation. And the Earth system is inherently nonlinear system in the sense that the amount of CO2 in the atmosphere is a function of the temperature, and the temperature of the planet is a function of CO2. So, it's much more complicated than that. There's more going on, but you immediately say, well, what's the chicken and what's the egg? Oh, well, there is no simple answer to that. It goes around and around and around.
It's nonlinear.
It is nonlinear. And so, to my mind, that's what makes it really fascinating. And again, part of how, actually, before I even started as an undergraduate in high school, I became interested in nonlinear systems and read the famous book Chaos by Gleick, and became very interested in fractal geometry and nonlinear systems within ecology and predator-prey interactions. And I took that with me out of high school into college, and so that's always been my interest, these solutions with no obvious, these problems with no obvious solutions. So, classic example would be predator-prey interaction, right? So if the number of wolves is a function of the number of deer, but the number of deer is a function of the number of wolves, you can have really complicated interactions. And that applies in the climate system as well. So if you replace wolves and deer with ice sheets, CO2, and temperature, the interactions can behave in much the same way. Understanding often comes from removing equations or removing parts of equations. So we know what the equations are that we need to write, and we've known those for some time, but they produce very complicated behaviors. And if we want to actually understand the solutions that we're getting, we oftentimes want to create simplified models. And sometimes those simpler models seem to represent reality better than the most sophisticated models, the ones with all the terms of the equation, which is a little bit counterintuitive, because you would think that as I write more and more terms in an expansion, or when I add all of the nuances and details to the equation, we might think that the behavior becomes more accurate. And that is the case some of the time. But in terms of these major transitions in the climate system, it's oftentimes the simpler models where we've reduced the number of equations and we've reduced the number of processes that we're including that seems to capture those better.
It seems that adding all these equations together, such as those for ice or glaciers or ocean currents or even atmospheric patterns, makes the picture a little too complex and hard to understand and predict our climate's future.
So I guess then by removing some equations and simplifying the schematic, scientists can create simpler models representing snapshots or like small bits of information.
So, Matthew, I heard you mention that there were complicated behaviors shown by your models. So, what were some of those behaviors?
So, for the past couple million years, the Earth system has been oscillating between glacial and interglacial states. So, the most recent one being the last glacial maximum about 21,000 years ago, where you have famously a mile of ice above Chicago. The climate system can get very cold, and those are called glacials. Then we have interglacials, where the world warms up substantially, and we've been in an interglacial now for the past 10,000 years. The behavior of the climate system coming out of the glacials and into the interglacials can be very rapid transition. You tend to stay in the glacials for a long time, so roughly 100,000 years or so. But the transitions out of them can be very, very rapid. And the whole system seems to transition at the same time. So you have warming, you have CO2 increases in the atmosphere, methane increases in the atmosphere, changes in dust, changes in the ocean circulation.
So it does seem that there's a relationship between these rapid transitions and the simpler models. So given the past that you know and have data for, and then your predictions for the future, do you think that the simpler models are doing better because the climate change we're experiencing currently is rapid in geologic timescales?
Yeah, I think that the very complicated, sophisticated models that we typically use with millions and millions of equations and every possible physical and chemical interaction operating in them, they're so complicated that it's like training wheels have been put on them, right? So, it's like, just imagine putting a really uncoordinated kid on a very fancy bike. It's going to go all over the place, and that's not the goal, right? So maybe they put training wheels on it. And unfortunately, I think that in many ways, with our most sophisticated models, for a long time, there were training wheels on them, which effectively what that means is that they were kind of more or less guided to not transitioning rapidly.
So you have the glacial periods and the interglacial periods, but we're going through, anthropogenic or human-caused climate change. How does that fit into the past interglacial periods Earth's experienced, and is it different?
Yeah, so we have just about released enough CO2 that we're going to kick out of those oscillations. So we've just experienced our last interglacial, and we're moving rather rapidly to the state that the climate system was like between 3 and 15 million years ago. And during that period, there was no Greenland ice sheet. Sea level was substantially higher, tens of meters higher. And the climate was between 3 and 7 degrees C warmer than it is today. So we've already added enough CO2 that unless we stop immediately, you can forget that whole glacial interglacial thing. Not going to happen again. We're punching through to a different climate state. And the Earth system has been in that state before. It's not like, oh, we go to Venus or, like, no, we've been through this. It hasn't been recent. It's been a long time. I'm not saying it's like, oh, we've done this before. It's no biggie. No, it's very big. We haven't done it in 3 million years. So it is, as far as most of what's around today, this will be pretty new. And so that's why this issue of transitions is so important, is if the change is gradual, then you can imagine evolution keeping up. You can imagine ecosystems keeping up. They've been through this before. It was a long time ago, but if you move slowly enough, maybe it's okay. And the kind of really sophisticated models that we use, they kind of have changes at a certain rate. It's pretty rapid, certainly compared to what we think has happened in some periods of time before. But if you do believe the simple models, and you do believe the paleoclimate records during the most abrupt transitions, then the climate models, even though they aren't that slow, may be still too slow. It's possible that transitions, when they happen even more abruptly than what our sophisticated climate models suggest. So a classic example of that would be sea ice. So sea ice in the Arctic. It seems like the models are transitioning to an ice-free state much slower than reality. And that's not very surprising to me, because I've actually modeled the periods of time in Earth's history when there was no ice in the Arctic. And models don't like to go there. So the kind of sophisticated models that I use, they tend to not be sensitive enough to CO2. You try and make the climate in those past warm climates, like I said, 3 to 17 million years ago or 50 million years ago, further back in the past. You try and get those climates. And the sophisticated climate models, you have to push them too hard. You have to add too much CO2 to get them to transition to that ice-free state. So that does kind of raise some cautionary concern on the part of me and many other people, that if those models you have to push them too hard, maybe the simple models are telling us the right thing, that transitions, when they happen, are abrupt. And you could go from having a fair amount of ice in the Arctic to zero ice in the Arctic Ocean, sea ice, I mean, in decades, rather than 100 years or 200 years. So that's the concern, is all of our sophisticated models are too stable.
Okay, so let me get this straight. The complex models are too sophisticated, or like too constrained by their training wheels to capture the real speed of climate transition, such as sea ice loss?
Yeah, and that was seen when modeling these past climates that we know transitioned so rapidly.
Oh, so scientists can use that knowledge to see that the complex models are probably underestimating the rate of current and future transition, and then turn to simpler models that have more availability to capture the speed of change?
Yeah, especially since we've removed ourselves from the glacial, interglacial system and are moving towards something new.
So I was wondering, how on earth, get it? How on earth? How do scientists even begin to model an entire planet?
What we do in these climate models is it looks just like Minecraft. We take the whole planet and we divide it up into these cubes. And the cubes are about 1 kilometer high and 100 kilometers on a side. And we solve the equations of motion and mass continuity and radiation within each one of these little cubes.
So in building these models, you mentioned paleoclimate data. What do those data look like and how do you get them?
Yeah, there's a wealth of paleoclimate data that's available. So people might be familiar with ice core records. So, you have scientists who go down to Antarctica or to Greenland or to small ice sheets in the tropics and drill into them and collect long ice core records, some of which can resolve changes in climate down to individual years, but perhaps more frequently tens of years of resolution. But they can record climate over tens of thousands to a million or a little bit longer than a million years. And those records, the ice includes, you can think of it as like a tape recorder or something that's just kind of every layer of snow that comes down takes a little snapshot of the atmospheric composition, so the amount of greenhouse gases like CO2, and also the isotopic composition of the air or of the snow itself, which tells you something about temperature.
So I'm curious to know, you take so much data to build these equations and build these models. Is there one specific type of data, say like methane versus CO2 or the lipids or fats that you mentioned that really seem to drive projected change?
Well, we don't really use the data to drive the model. We use the data to test the model. So we do need some data to drive the model. So I'll give you an example. When I do paleoclimate modeling, I'll work with experts in geology and mountain building and bottom of the ocean, the geophysics that determines the depth of the ocean, work with paleobotanists, and we'll create a map of what the world looked like 35 million years ago or 55 million years ago. And so that set of maps is what we call boundary conditions. And the models that we use, you have to input the boundary conditions. So the boundary conditions include like the height of mountains, where the continents are, the depth of the oceans. And some of the other important boundary conditions include things like what was the atmospheric CO2 concentration? What was the atmospheric methane concentration?
So when you say boundary conditions, that's like the height of the mountain and things like that. Is that what makes these models more complex when you say simple versus complex models?
Yeah, that is definitely one of the things that makes those models more complex is they can capture all of the details of the boundary conditions. So they're spatially resolved. So we're we're modeling the temperature and the wind and the precipitation and the radiation in little boxes all over the planet. And those boxes might be 100 kilometers on a side or something. Whereas in a simplified model, the whole world might be represented by 4 equations. And that's it.
What are those equations?
Well, you start off with Newton's equations. So you start off with, equations for the motion. So the momentum equations. You add in continuity or mass conservation. And then, you do this on a rotating sphere. So you have to include the fact that you're on a rotating planet, a rotating spherical planet, and you have to have radiation and gravity. Gravity is your good friend. So that sets up like the overall set of equations we would call the primitive equations. And that's always the starting point. So whether it's a complicated model or a simplified model, that's your starting point. But then it's how do you simplify that model or not? And if you go complex, well, then you end up with these very big, sophisticated but complicated numerical models where we represent things in little grid cells over the whole planet. You can also take that and dramatically simplify it to just a couple of equations. And one of the more famous set of simplified equations would be the so-called Lorentz equations. And, that's the person who named the butterfly effect and is a foundational person in the field of chaos theory. So, again, if you If you take the complex, sophisticated equations, but you filter them and you really, really simplify them, you get chaos and catastrophe.
Why, if I may ask?
None of that explains why. There's very little why in science.
Hey, that's your job though, right? Figuring out the why.
So without math, we have chaos and catastrophe.
Yeah, 100%. And I'll need to remember that when Olivia gets old enough to do math and she doesn't want to do it. I'll explain to her why it's so important.
Yeah, I mean, it's a good overall reminder that sometimes in life we need to do things that we don't want to do.
Well, certainly not this podcast. I like doing this podcast contrary to what you think, Shane.
For the record, I like doing this too.
Good.
Well, thank you to both of you. I very much enjoy it as well. It's more than just the job, and I'm so happy to be here with y'all. So with that, we'll end on a high note, and that is all from Third Pod from the Sun.
Thanks so much to Jessica for bringing us this story and to Matt for sharing his work with us.
This episode was produced by Jessica with audio engineering from Collin Warren and artwork by Jace Steiner. And be sure to head over to the Carry the Two podcast next week for more from Matt on the math and stats front.
We'd love to hear your thoughts on the podcast, so please rate and review us, and you can find new episodes on your favorite podcasting app or at thirdpodfromthesun.com.
Thanks all, and we'll see you next week.
Oh, so scientists can use that knowledge to see that the complex models are probably underestimating the rate of a future climate transition and then turn to simpler models. Nope, Shane's shaking his head. You're screwing me up. You screw up so much that you're screwing
I am literally sitting here not saying a single word. I'm not even making a face. I'm just I'm just reading the script.
I can't see you.
You can turn my camera off. Like you can opt
I can't.
not to see me.
No, then it'll just be too weird.
Oh, you're just,
I'll just be talking
voice.
to the.
You'll be talking. I'll just be like, Vicky.
Don't do that. Stop.
I didn't do anything. I'm sorry.
Okay. All right.